Inference for linear regression. To examine the effect that a quantitative independent variable has on a quantitative dependent variable, we use simple linear regression. Please recall that in a previous video, we used simple linear regression only for descriptive statistical analysis when we examined the relationship in terms of form, direction, and strength. We still check form on our scatter plot, looking for either a linear or nonlinear relationship. Direction is still indicated by our slope, and the strength of the linear relationship can be explained by the correlation coefficient R. If we report the regression equation as shown, we would use R squared, the coefficient determination, as a measure of effect size, which explains the percentage or how much of the variability in our dependent variable is explained by the regression equation. We can easily use the Excel tool Inference for Regression to run simple linear regression. All we need is to input variable numbers for both the independent and dependent variables. The worksheet Simple contains all of our descriptive results, including our equation and R squared. The worksheet Inference 1 now contains important significance results and forecasting tools. Our worksheet Residuals is still used to check for regression outliers, only now we'll also use residual analysis to check important model assumptions. Residual analysis is used to check for regression outliers. Please recall that regression outliers are extreme residuals and weaken the overall linear trend. They're also defined by the expression y minus y hat for a particular x value. In general, less residual indicates better fit or a stronger overall linear relationship. Our worksheet Residual will still flag any residuals with z-scores beyond positive or negative 2.6. Residual analysis is also used to check if the regression model assumptions are met. The regression model assumes two things: a normal distribution of residuals and what we call constant variation of residuals. Here we see three residual plots. The residuals should show constant variation with a random distribution around 0, like we see in the top plot. Drift indicates that the variation in our residuals is not constant, like we see in the bottom plot. We can see that the residuals systematically increase as the value for x increases. In the middle, we see a clear pattern on our residual plot. We should see no pattern with a random distribution around 0. Remember, our NQ plot of the residuals may be used to check for the normal distribution of residuals, also a required assumption. Let's go to our Excel tool now to practice using our simple linear regression tool. Remember, we need an independent variable and a dependent variable that are both quantitative, such as age and amount charged. Let's look at our results. On the Worksheet tab Simple, we can see that age and amount charged have a moderately strong linear relationship with a correlation coefficient R of 0.5850. Our regression equation shows that predicted amount charged, y hat, is equal to $58.69 times age plus the y-intercept. And this equation explains about 34% of the variability in spending. Let's check our residual plot to see if the model assumptions are met, which is a condition for making inference for regression. First, our NQ plot shows a normal distribution of residuals. That's one required model assumption. Also, we can see on the residual plot no clear pattern and no clear drift. Remember, we're looking for a random distribution relative to that 0 line. Let's try another one. Remember, we need a quantitative independent variable like income. Let's check our results. Income also shows a moderately strong linear relationship. Again, it's positive with a correlation R equal to 0.6249. This equation explains a little bit more, 39% of the variability in spending. So we can also see that as a single predictor of spending, income is a little bit better than age. But let's check our residual plot. Our residual plot looks good with no clear drift and no clear patterns. Again, we can see also outliers on the residual plot, but our spreadsheet will flag those according to the z-score. Finally, our NQ plot shows an approximately normal distribution of residuals. Remember, it's possible for us to observe a strong or moderately strong linear relationship between two variables, but for that relationship to be tied to only one sample of data. Therefore, before we could use our regression model for forecasting, it's important to check the significance of the linear relationship between the two variables. The population slope may be estimated using the familiar 95% confidence interval. If the population slope is not likely equal to 0, we would conclude that there is a true slope, or in other words, a true linear relationship between the two variables. We rely on the t-distribution once again with n-2 degrees of freedom. And we can see that our confidence interval is calculated as our sample slope plus minus the appropriate margin for error. In addition to our confidence interval, we can simply test the significance of the linear relationship by using a t-test for the population slope. In this case, the null hypothesis would be that beta 1, the population slope, is equal to 0. If we can reject that null hypothesis, we would conclude alternatively that beta 1, the population slope, is not equal to 0. If the slope is not equal to 0, there's some slope, or in other words, some true linear relationship between these two variables. So either the confidence interval for population slope or the t-test for slope may be used to test the significance of the linear relationship. In either case, we're trying to determine that the population slope is probably not 0, and therefore a true linear relationship exists. Let's go back to our Excel tool now to practice using our methods to check for the significance of the linear relationship between two quantitative variables like age and amount charged. We've already seen that there's a moderately strong linear relationship between these two variables. However, this is just one sample of data. It's possible that we could observe a linear relationship in this sample when there's not a true linear relationship in the entire population. Our worksheet tab Inference has our results. First, we can see from our confidence interval that we're 95% confident that the true slope beta 1 is somewhere in the range 43.098 all the way up to 74.285. Most important, we can see that 0 is nowhere within that range. So it's like saying we're 95% confident that the true slope beta 1 is not 0. We can also use our t-test for slope. Here we can see that t for 107 degrees of freedom, remember our sample size n is 109, and our t-test uses n-2 degrees of freedom, simply because we have two variables, x and y. So t for 107 degrees of freedom is a very strong 7.46. The probability of getting that much slope at random, if we assume as a null hypothesis 0 slope, is very close to 0. So there's virtually no chance that the true population slope is 0 given a sample slope of $58.69. Let's try another. We also looked at income, which is variable number 1. Our worksheet tab Inference 1 has our results. We're 95% confident that the true slope is somewhere in this range. Most important, we could see that 0 is clearly excluded from that range. Once again, our t-stat of 8.28 produces a p-value very close to 0. So we strongly reject the null that beta 1 equals 0 and conclude alternatively that there's a true linear relationship between these two variables. Now that we have checked that the regression model assumptions are met, and we've checked that the linear relationship between our two variables is statistically significant. So now we can use the regression model for forecasting. We have two tools. They're both interval estimates, like our familiar confidence intervals, but we give them different names. The term prediction interval usually refers to a forecasting interval for a single outcome, while the confidence interval refers to an interval estimate for an average outcome. For example, below we can see two forecasts. One is a prediction interval and one is a confidence interval. The prediction interval, we would say we are 95% confident that spending for one cardholder with an income of 125 is somewhere in that range, while the confidence interval makes a forecast for average spending for all cardholders who have an income of 125,000. The prediction intervals are much wider because forecasting a single outcome is harder than forecasting an average. Yet, operationally, both are needed. Let's go back to our Excel tool now to practice using our forecasting methods for simple linear regression. Let's start with the regression of age and amount charged. The worksheet tab Inference 1 has our two forecasting tools. First, the confidence interval for a mean response. Let's input an x value of 28. The y-hat value is simply $3,581.53, and we get that from our regression equation. Let's look now at the prediction interval. Again, we'll input the cardholder age of 28. And we can see that the y-hat value is exactly the same. This will always happen. Both forecasting intervals will have the same y-hat value. However, they have very different margins of error. The prediction interval gives us a range at 95% level of confidence for the spending of one 28-year-old. In other words, we're 95% confident that a particular 28-year-old cardholder spends somewhere in the range $2,000.53 up to about $5,162.53. On the other hand, our confidence interval makes a forecast of average spending for all 28-year-olds. And we would say that we're 95% confident that average spending for 28-year-old cardholders is in the much narrower range, $33.73 and 76 cents, up to $37.89 and 29 cents. Let's try another. We also looked at cardholder income, which is variable number 1, and we've already checked that the regression model assumptions have been met and that the relationship between these two variables is statistically significant. Now we can use our forecasting tools. Let's forecast given a cardholder income of $125,000. Our prediction interval shows that we're 95% confident that spending for one cardholder who has an income of $125,000 should be in the range $24.90 and 34 cents up to $5,522.12. Our confidence interval, on the other hand, shows that average spending for all cardholders who report an income of $125,000 should be in the much narrower range, $38.59 and about 8 cents up to $4,153.38.